Okay, good morning. Welcome back. Happy Friday. Today we are covering algebraic fractions. This is day 2 of 3, although on the 4th day we're just doing more fraction stuff. It's going to be equations though. This is the entirety of what's left in the semester. This coming week we've got our 3rd day on algebraic fractions. Wednesday we're going to do equations with fractions in them. Friday, a week from today, is our 5th and final quest. It's only on the fraction stuff, so these 4 lessons that are up here. Wednesday next week is that's not right, that's Friday of next week. Monday, the 16th, is the last day of the semester. Review day, we'll just talk for 5 minutes together about the final exam generally and what resources you have and what you might do to prepare. And then you'll spend the bulk of Monday's class just studying however you see fit. And then Wednesday, the 18th, is our final exam. Questions on the calendar. So just reiterating, much better to find little chunks of time regularly between now and the exam than to count on studying for 6 hours the night before the exam. That's not a good strategy. Right? 20 minutes a day, that's a lot healthier. Okay, so let's go to page 237 and start with our daily summary. In this lesson, we continue our work with algebraic fractions to include adding them and subtracting them. Recall last class what we did was take a single fraction and simplify it, and then take 2 fractions and multiply them, or 2 fractions and divide them. Turns out adding and subtracting is harder than multiplication and division, so that's what we're doing today. The demo is a little long. We'll try to get through it as quickly as possible so you have lots of time to practice. Starting with number 1, let's take a moment to recall how we add and subtract fractions with like denominators. If you saw 2/3 plus 5/3, what would you say the answer is? 7/3, right? But I'm going to put this step, which you would never normally put. You would just in your head say, oh, 2 and 5 get to add together and make 7. And what makes this an easy addition of fractions problem is that they already have a common denominator. And notice that you just keep that common denominator. It doesn't become 6 or 9 or anything like that, right? Okay, so adding and subtracting fractions with like denominators, common denominators, works the same way for algebraic fractions. Let's try this calculation right here. This guy equals. So looking at the 2 fractions, what do you like about those denominators? They're the same. And so this is the easy kind of problem because they have the same denominator. So when I push them together into 1 fraction, what's the new denominator? 3x plus 4, just a copy of it, just like the thirds in the previous example stayed thirds. Okay, upstairs. I'm just going to push these 2 guys into a single fraction. It's tempting to start combining like terms. It's okay if you do it carefully, but I don't think I need to do 2 steps in one, so I'm just going to copy 9x squared minus x minus 3x squared minus 9x. Everybody see what we did? It's a small step. Might seem silly, but I think it's an important one. We're going to catch some mistakes by just writing that step. Okay, equals. All right, so let's combine terms. What do we get for the x squareds? We got 6x squared, right? And how about the x's? Negative 10x. And the denominator? Same thing, 3x plus 4. Okay, this is wrong, but it's really easy to make the mistake that we made. And if you buy that this is the answer, then I convinced you that we did something that was legal, which was not, Jeff. We didn't. That's exactly the problem, is that this subtraction sign says you are subtracting this entire thing, right? That whole bag of stuff is getting subtracted. But somehow the only thing that ended up getting subtracted was the 3x squared, because that minus 9x didn't get subtracted. It just got shoved over there as it was. So, common mistake. It is wrong. How are we going to fix it? Yeah, and I'm going to do that in 2 steps. This is my recommendation. Strong recommendation is that when you go from 2 fractions to the single fraction, you just put parentheses as a rule every single time. So then we're going to fix our numerator up here. I'm going to copy the first guy without parentheses. And now the second guy, that subtraction symbol changes all the signs inside. So it's still minus 3x squared, but then plus sin x. That's what it should have been. You guys see how easy it is to make that mistake, right? So just put those parentheses every time we go from two fractions to a single fraction. Okay, so now we can combine like terms here. So denominator was correct. 6x squared is still correct, but now for the x's, plus 8x. That's right. And oftentimes that's the final answer. But last class we talked about taking a single fraction and simplifying it, and that is our obligation. Like you would never on a quiz or a test leave 3/6 as a final answer. What would you write instead? 1/2. You just do it as a matter of course. Well, it's the same thing here. You're not going to leave that if it's not simplified. So if we can reduce it, we have to. So in order to reduce, what do we do here? Let's see. So I see a 6 and a 3, so we'll make a 2 and a 1. Let's say I got x squared up here and an x down here, so we can get rid of those. All good? Any of it good? Nope. So remember there's a lot of things that look like they could cancel, but they can't, because the only time we can cancel is when we have multiplication, not addition, not subtraction. So we got a factor. Equals. First kind of factoring always is the greatest common factor. What is it on top? 2 and also x. That's the key. And then what's left? 3x plus 4 divided by, on the denominator, I'll try to factor it if I can. Greatest common factor is just 1. It's not a difference of 2 squares. It's not one of our trinomials where we use the box. So not doing anything with the bottom, just copy it. And now that we're factored, is there anything we can cancel? The 3x plus 4, which is a carbon copy upstairs and downstairs. Technically, what do I have to replace the bottom with? With a 1, right? And we're not going to write it, but when you cross things off, they become 1s. So 2x over 1, which is just 2x. Questions on that one? What's that? Yeah. Uh-huh. And I'm going to try to continue to make the common errors, and you're going to continue to call me out on it. All right? Okay, so easy if the denominators are the same. Significantly harder if the denominators are different. So that's what we're going to spend the rest of our time on. Number 4, we now add and subtract algebraic fractions with unlike denominators. We'll use the idea of building the LCD, lowest common denominator, by filling in what's missing. And we're going to key in on that idea of missing in this example right here. So let's take a look at this, this problem. This is just arithmetic, only numbers, and then we'll do it with x's and y's. Okay, so we got 9/28 minus 3/40 minus 1 over 42. 3 fractions, all add and subtract, all subtract here. Denominators are different, so the first task is to find the common denominator. 28, 40, and 42. Can you guys think in your heads, or even if I gave you a calculator, what the lowest common denominator is for 28, 40, and 42? The smallest number that they both go into, what'd you say? 2? Well, 2 goes into all of them, but what I'm looking for is a big number that they all go evenly into. It's going to be quite large, and not something that I personally can do just on the top of my head. If you gave me small denominators, I could do it. Like if you gave me a 4 and a 6, what's the lowest common denominator if one denominator is 4 and the other is 6? 24 is fine, but smaller is 12, right? And so just 4 and 6, I can say, oh, they both go evenly into 12. Those numbers, goodness gracious, even 2 of them would be hard for me, and now we got 3 of them. So we're going to give you a way to do this that will carry on and help us as we do it with x's and y's. First step is to factor the denominators completely. So 28 is really 2 times 2 times 7. Agree? We factored all the way down to what kinds of numbers there? What are they? The prime numbers. That's how you know when you're done, right? You can't go any farther than 2 or 7. 40 is equal to 2 times 2 times 2 times 5. Do we agree? Just factor it. Maybe you might have made like a factor tree back when you were doing factoring. 42 is 2 times 3 times 7. Agree? Okay, now that the denominators are factored, we're going to make all the denominators the same by filling in what's missing. And notice that there's some blank spaces I've left in my fractions here. So let's just focus right now on the first two denominators. Don't worry about the third one at the moment. What is the second denominator missing that the first one has? What number? 7. Yes. The second denominator does not have a 7, but the first one has a 7. So what we're going to do is we're going to multiply the bottom right here by 7. But you can't go around willy-nilly multiplying the bottom of a fraction by 7 without immediately doing what? Multiplying the top by 7. So times 7 right up there. What have we just filled in? That 7 over 7, what was our funny name for that? It's a foo-foo. That is a fancy form of 1, and it's one of the few things that you're allowed to do, right? You're allowed to multiply by 1. Okay, so times 7 times 7. Super. What is the first denominator missing that the second one has? It's a 5. And you better right away multiply the top by 5 as well. Are the first and second denominators exactly the same right now? Don't worry about the order, but are they equal? They're not. What else is the first denominator missing? It's another 2. Even though it's got a couple of 2's already, it needs 3 of them. I need these denominators to be the same, and I'm not allowed to remove any. All I can do is multiply by more. So we are also going to multiply by 2 on top and bottom. If you look carefully at those first two denominators, what do you notice? They're the same. That's what we accomplished. So we understand this idea of filling in what's missing. You look at one, give it what it's missing compared to the other. Okay, the third denominator has been left out in the cold this whole time. Let's complete it. Third denominator compared to, well, you can compare it to either of the first two denominators because now they're the same. Great. So what is the third one missing that the second one has? So it has a 7. So it needs a 5. So let's give it a 5. What else does it need? 2 more 2's. So give the third denominator a 5 and a 2 and another 2. Wonderful. So are our 3 denominators the same now? No. What we did was give the third one what was missing, but now that the third one is in play, the first 2 might be missing some stuff. What are the first 2 denominators missing that the third one contributes? Is a 3. And so we will give a 3 to the top and the bottom here, and a 3 to the top and the bottom there. And now what can we say about all 3 denominators? They're all the same. Okay, so all the stuff that we just did with the filling in what's missing is written out here, and there's stuff circled and foo-foos and things. So you can read that later, but we just did it. And we're just going to skip to finishing this problem. So on the next page, the first expression here at the top is exactly what we just had. And then it's just a matter of multiplying stuff out. So the arithmetic is already done here, but 9 times 2 times 5 times 3, apparently that's somewhere 270. So 270, and the next one is a 63, and the last one is a 20. And the denominators turned out to be, I don't know, 840. So 840 was the lowest common denominator. Jeff said it may be in the thousands, so that wasn't a bad guess. 840 is the smallest thing that all 3 of those denominators went into. And then it's just a matter of smushing them together into a single fraction, right? We had 1, 2, 3 fractions, and we just pushed them over into a single fraction. Notice that we put parentheses around each of the things that were original fractions. And then we just do our subtraction here, and we get 187. And we should check and see if anything cancels, like we should reduce our fraction. It turns out nothing does in this case. So 187 over 840. So that example is supposed to remind us of how adding and subtracting with different denominators works, but also to give us a way to handle it when the denominators are kind of a lot more complicated than, say, 4 and 6. So let's see if we can take those ideas and apply them to algebraic fractions. So here we go. Part B has this addition and subtraction of 3 fractions. I've written it out here just copied. And what do we notice about those denominators? They're different. Well, that's unfortunate because we're going to have a lot of work ahead of us to make them the same. And I just want to point out at this stage right here that, for example, if you wanted to look at this 3y plus 4 and you want to make a common denominator with this y minus 5, it's tempting to maybe say, okay, let's see, how can I turn this minus 5 into a plus 4? Well, I guess I could add 9, right? Because if you add 9, we get y plus 4, yeah? Which is starting to look closer to that guy right there. Well, adding 9 to the denominator is not allowed. There's just no universe in which we can add 9 to a denominator. Adding 9 to the numerator doesn't fix it. You can't add 9 to top and bottom. It changes the fraction. What's the only thing we're allowed to do to top and bottom is multiply. So don't ever think about adding or subtracting. To try to make these denominators the same, it is never about adding or subtracting because it's just not allowed. So what we're going to do is end up multiplying stuff. But first thing we want to do is factor. Just like we factored all those denominators before into their primes, we're going to factor here. Y minus 5, there's nothing to factor. 3y plus 4, there's nothing to factor. But what kind of factoring do you think on the 3y squared minus 11y minus 20? Greatest common factor is just 1. Difference of 2 squares, not in play. What's left is the box. So again, we're not going to take our time doing the box, but I will tell you that I've already done the box, and that's what I got. So factor first. It's the right way to begin these problems. Just the denominators. Notice that we pay no attention to the 7y squared plus 24y plus 28. You might be able to factor it with a box, but even if you can, it's not going to help us. So it's only about the denominators. Okay, so I've copied my fractions over, but one of them is now in factored form. I've given myself some extra space on these fractions so that I can complete those denominators. So looking at the first fraction, what is it missing that the second fraction has? And the answer is 3y plus 4. The entire thing. The second denominator is 3y plus 4. That has nothing to do with the first denominator. They both have a y in them, but that's it. So we are going to multiply the bottom by 3y plus 4 and therefore the top by 3y plus 4. We're missing parentheses in a lot of places now. We didn't need all of this when it was just numbers in the previous example, but we've got some binomials with additions and subtractions. So we need parentheses everywhere now. Okay, what is the second denominator missing that the first one has? Y minus 5. So go ahead and put it in with lots of parentheses. Technically, the 4 didn't need parentheses, but it's safest to just put them everywhere. Okay, what can you say about these first two denominators? They're the same, and the way that we built them was the simplest way to make them the same. You cannot add to make them the same. You cannot subtract to make them the same. All you can do is multiply. Okay, so the first two denominators are great. They're the same. Now we're going to look at the third denominator, and we're going to say, what does this third denominator need that the second denominator already has? The answer is nothing. We actually kind of got lucky. What can you say about all three denominators? They're the same. But notice that if we had left this original denominator in this form without factoring it, we wouldn't have recognized that this denominator was the same as the first and second ones have become. And so if we left it as a 3y squared minus 11y minus 20, we might say, oh goodness, this denominator right here, the first one, needs all of that 3y squared minus 11y minus 20. And you put it on the top and you put it on the bottom, and all of a sudden you make the problem impossible for us to do. It's really important to factor so that you can see what's in common and what's missing. Okay, so all three denominators are the same. It turns out there's still a bunch left to do in this problem, but at least we've got the first step where all the denominators are the same. So here's the next step, equals. So let's write this here. One big fraction line, and we're going to make a single fraction where there once were 3. What's the denominator for this new fraction? y plus 4, and y minus 5, right? Just a single copy of it, not 3 copies of it. And then I think it's important to just copy those numerators as they are, but just put them into one numerator. So the first numerator with all the parentheses. What's that? What's the next symbol? Plus. We're adding, and then you copy the second numerator with all the parentheses. And the last numerator, what's the next symbol? Subtract. So we go minus 7y squared plus 24y plus 28. So far, so good? Yeah, I'm not calling on you again. Everybody else okay? Jeff is not okay. Is everybody else all right? Break it down like factor it. So we actually don't need to factor that, and we'll see why in a second. Yeah, so factoring it is not going to head us in the direction we want to go. Do we need parentheses around it? It didn't have parentheses before. This guy has no parentheses right now. Do I need it? Why do I need it? Because the whole thing is getting subtracted, right? This entire bag of stuff is getting subtracted, but it's not in the bag anymore. You could tell it was in a bag because it was its own fraction before, but now that it's part of another fraction, it lost the bag, and so we need to give it a bag. Subtract the whole thing. It's really easy to miss this. Okay, so now it's time to start distributing. Word to the wise. It is tempting, maybe, to start canceling because we got some stuff on top that's the same as stuff on the bottom. Look, 3y plus 4. Fantastic. Cross it off. Y minus 5. Wonderful. Cross it off. Hey, the fraction's not even there anymore. This is great. What's the problem? Why can't I cancel? Yeah, the top has addition and subtraction in it. You can't go around canceling when it's addition and subtraction. Even though this is a multiplication, that's not the fundamental operation on the top. Fundamentally, it's an addition and a subtraction. So we can't cancel there. The real problem is that you're always going to have this temptation because the 3y plus 4 on the bottom you put on the top. So like you went out of your way to put it there. So you'll always have an opportunity to cancel because you put the same thing on top and bottom, but don't. So what we do need to do is distribute on top. So either lobster claw or foil or make a 2x2 box for multiplying. We're just going to write the answer here. So we go 9y squared. I'll do the outers and inners together. Outers is 12y. Inners is 6y altogether. 18y. And then the last is a plus 8. And then we'll just distribute the 4. So plus 4y minus 20. Then we'll distribute that subtraction sign. So just change all the signs. Minus 7y squared minus 24y minus 28. All divided by, and then we're just copying that denominator. Now, we did all that distributing on the top, and we're going to see why we did that on the top, but it turns out distributing on the bottom not only takes time, but actually makes it harder to simplify your final answer. So the rule of thumb here is never distribute on the bottom. Just leave it in factored form, even in your final answer. I won't be surprised to see factored things, not distributed things. But the reason we distribute on top is that all of a sudden now we have like terms, right? 9y squared minus 7y squared. We can smush them together and get a single y squared term, right? That's why we distribute on top, because there's going to be like terms that maybe combine. But on the bottom, there isn't going to be anything that like cancels or combines. You're just going to distribute and it'll get bigger. Distributing on the top makes things bigger, but now they're about to get smaller. So what do we get here? How many y squareds? 2y squareds. So I'm just going to put little check marks for the guys that we've dealt with already. And now looking at just the y terms. So I've got 18 of them there, another 4 is 22 of them. And then, so it's negative 2, negative 2y. Okay, and then finally the constant terms. There's an 8, there's a minus 20, and there's a minus 28. Negative 40 sounds good to me. Okay, and then just copying the denominator. Do not distribute down there. I know it's weird to do different things on top and bottom. I'm saying distribute on the top and don't distribute on the bottom. That's kind of asymmetric, which you don't often find in a math class. So I'm hoping that I've made it clear as to why we should distribute on the top, because even though temporarily it gets bigger, it just got compressed way down. In a second, we're going to see why we don't want to distribute on the bottom. So this might be our final answer, but if we can simplify that single fraction, then we're obligated to. Again, you would never leave 3/6 as a final answer on a math test. This might be something like that. So we're going to try to factor. First kind of factoring is always greatest common factor. What is it? 2. Super. Let's pull the 2 out. So that leaves y squared minus y minus 20. Copying that denominator. And the thing in the parentheses maybe factors more. We've already done the greatest common factor. Is the thing in the parentheses a difference of 2 squares? Nope. Is it a box? Maybe. Sure. I mean, it looks like the ones where the box works, right? So I'm going to put, we're going to hide the details here. Dot, dot, dot. Use the box, but I'm just going to write the answer here. So the thing in the parentheses turns out to factor. Anybody know how to do this? Plus 4 and minus 5 is correct. So details are omitted there. Divided by, copying that denominator, 3y plus 5. Oops, yeah, y. Something happened. Why did that become a 5? Let's try that again. 3y plus 4, right? That was another intentional mistake that just like the ones I've been making. Okay, can we cancel anything? We can. What do you know? Y minus 5, same on top and bottom. So our final no fooling answer is 2y plus 4 over 3y plus 4. After all of the brilliant work we did on this problem, don't you dare cross off those 4s. You'd be surprised how often people get to the right answer and then they do illegal stuff at the end. Third question, Jeff. Give me one problem. There it is. Take an hour and do this one problem. Yeah. Now, the fact is, in the demo, my rule of thumb is to try to give you the hardest kind of thing possible. So when you start in the activity, they're going to be a lot more straightforward than this, but they will build to this. That's as hard as they get. I mentioned that we don't distribute on the bottom. Do you see why we didn't want to distribute on? If we had distributed on the bottom, we wouldn't have seen that we could cancel, and you just have to factor it back, okay? So that's why we do different things on top and bottom. Okay, so last example, we'll just do the highlights of this one. We won't do the whole thing. So for part C, it says the next one requires that we correctly handle repeated factors, and here's how we do it. So this one just has 2 fractions subtracted. The first fraction we're going to factor. Again, greatest common factor is always first. What comes out of both? X. And so you can see I've written X on the outside of X minus 1, so that's factored. And then the next guy, this X squared plus 4X minus 5. Not greatest common factor, not difference of two squares, but the box. So I'm just going to underline in red that this guy has become this guy after using the box, okay? And the x minus 1 is just copied, underline in green, it's just copied over here, all right? So denominators are factored completely. That's the first step. Got to factor those denominators. And now we're going to figure out what's missing. What is the second fraction missing that the first fraction has? It's x. That x way in the front. The second fraction has lots of x's in parentheses, but it doesn't have an x sitting by itself. So we give it an x on the top and the bottom, which means you're also introducing some parentheses. Okay, now let's look at the first denominator. What is the first denominator missing that the second one has? X plus 5 for sure it needs, right? X plus 5, top and bottom. Just for good measure, I'll give the 4 parentheses too. Are these two denominators the same now? They're not. The second guy has x minus 1 and another x minus 1. The first guy just has a single x minus 1. So what do we give the first guy? Another x minus 1. Top and bottom. Now the denominators are the same. Okay, so repeated factors, just have to make sure you give each denominator enough copies of the thing, even if it's more than one. We're not going to finish this one, but you would do the distributing on the top. You'd push them together to one single fraction. You'd combine like terms and simplify your final answer. The work is done out there. Any questions on that? Jesse? No, there is an addition between. It's hard to see. There's a subtraction symbol. Yeah, but I really like that because I mentioned that you're always going to have an opportunity to cancel. And you can cancel right now. Like you can totally cross off, look, x plus 5, x plus 5. I can do that, can't I? It's all multiplication. But why shouldn't I do that? You're undoing your work. You put the x minus 5 downstairs intentionally to make a common denominator. If you cross them off, you don't have a denominator that's the same anymore, right? So like it's legal to do that, but you're going the wrong direction. So we have to avoid that temptation. And we're going to have it on every one of these addition and subtraction problems. Okay, so I think that is the demo. Go ahead and start on the next page and I will walk around.